I skip anything? Let's see. No, we're fine. So now, I still don't see the slideshow icon down here. It used to be down there, right? How come it's not there today? Okay, then indicator, color indicator, right? So we are talking about redox titration. So now the indicator is going to participate in redox reaction, okay? So the indicator is a chemical, so this chemical is going to be exist either in oxidized form or reduced form, okay? So when it is in an oxidized form, there's one color. Then when it is reduced form, then it's another color. So this is at equilibrium, so it must be the first criterion is that this chemical between the two forms must be reversible quickly because it involves in titration. Okay? So now, this is the first criterion. Then we will talk about the second criterion later, that when you have a mixture, then once you reach the end point, there will be a potential in the mixture. So once the potential at the end point matches the potential for this equilibrium, then that's the time you get a color change. Okay, just like pH indicator, you need to match the endpoint's pH by the pKa value of the indicator. Same here, so there will be a potential associated with this indicator. Okay, so there are not that many good indicators, and these are the two important types because they have potentials of within this range, and this range is very common in redox titration. Okay. Okay, so it must be quickly reversible. Okay, so the indicator itself, the chemical, so when it's one chemical, then it will have a half reaction. So this represents its half reaction. Then when it has a half reaction, then it must have a E naught, right, reduction potential. Okay, then your experimental potential, then this is the endpoint's potential. We try to match for the experimental potential of the indicator. Okay, so you can call that, because we are picking an indicator, then this is the endpoint's potential. Okay, to match for the E naught for the indicator. Okay, so this is the formula. You want the closest match. Then the rest is just concentrations of the indicator for your color change, right? So color 1, color 2. So when it's 1 in oxidized to 10, then it's for sure you are seeing the color 2. And then here the other way around, 10 to 1, then you for sure seeing color 1. So when it amounts to the concentration ratio, this is the uncertainty. This is transition range. Okay, you want this coverage to be far enough so that you can see the change. Okay, so here, start from this point, 1 to 10, then for sure you're seeing one color, and then at this ratio, for sure you're seeing another color. So this is the at least, the least desirable, or at least the desirable range. Okay, so it turns out that, so from here to here, okay, that range is plus 0.059, here's a minus 0.059, so the indicator should cover up at least a range of 0.12 volts. Okay, so your endpoint should be within at least this range. So here is a continuation of that. So I plug in the 1 to 10 and 10 to 1 ratio. Then you will get this deal, okay? And end up with that. Okay? So follow this calculation, 1 to 10, right? And here, continue with that. You know, this is incomplete, so you just multiply the log of that ratio. Okay, so when you review this topic, do that calculation and end up with this value. Any question? Okay, we have talked about using electrodes to determine cations, metallic cations. Well, there are electrodes for detecting anions as well. Okay, so remember, this is a typical example. So the conductor is a silver wire, and your analyte is an anion, which is an iodine, so minus. So once the wire stick into that, then there will be an affinity. So there will be a thin coating of silver iodine precipitate on it. So this is your electrode, the entire assembly. Then you look up the half reaction, then there will be a match. So here is the conductor, the silver wire, then here is that coating of precipitate, and this is the free iodine. Okay, so when you see a half reaction, actually you can come up with your own setup, your electrode. Okay? So when you look at this, then you can write a half reaction to represent that based on the Nernst equation, right? So this is a Nernst equation, this is an experimental potential, right? Then this is an E naught. You look up the table, you know, the E naught is equal to this. So you plug that in, E naught, and then put the minus in front, then your Nernst equation, then this is the I minus concentration. So as you can see, you know, this is an unknown based on the potential. So now you can simply measure the potential, leads you to realize the unknown concentration, right? So theoretically, this becomes a value, experimental value, then you can calculate for the I minus, okay? In reality, it's a standardization procedure. You need to calibrate to get a calibration line. Okay, so the minus log is the same thing as the P function, right? So this can be reduced into reading a potential, then you get the P value for the anion. Okay, so remember this application. Yes.
0.591 pi?
The Nernst equation, whatever that constant is.
What is that? Isn't it just 0.59? Times pi?
Yeah.
Right there, that little
Yeah, when you expand the scale, the decimal place.
Oh, okay, so it is.
Yeah.
So 0.591.
Yeah, usually you just start with a 0.59. Okay. Any other observations, question?
And then you said E was just the experimental value, right?
That's right, yeah, you just measure and get that, while the E naught is a table value as a reference point for you to extrapolate.
I already.
Okay. theory of redox reaction, there are limitations. Okay, so we've been talking about that when you have 2½ reaction, then you have a potential here, and you have a potential here, right? One is reduction, one is oxidation. Then when you combine the two, to get a E overall, as long as you get a E overall as a plus, then you say that it is spontaneous reaction. Well, the statement is true, but you don't know the rate of this spontaneous reaction, whether it goes fast or it goes slow. For example, here, you will get old. You get older for sure. That is spontaneous reaction. You will not get younger. I wish I could. Einstein philosophy comes in. If I could turn the Earth opposite way, go back. But that's not spontaneous. You need Superman to do that. Move that backward. That is not spontaneous. We are talking about spontaneous reaction. So this is spontaneous, right? So this is going to be a plus. But then how fast it goes, that'll be slowly, right? So getting old is a slow process. So that is slow. Okay, so whenever you do that, you get a delta E, right? Simply the delta between the two, so-called the delta, that is a minus in between the two, then that means switch one of the two from reduction into oxidation. That's what it amounts to. Then you combine the two, then you end up with a plus, then whether it's fast or slow, you don't know. So there's nothing to do with the magnitude. Even though it has a plus, they say, okay, the higher magnitude, then the faster. It's not the case. It's not that. Okay, so keep that in mind. So that is being a limitation. Okay, any question? I'll further